Hello everyone and welcome to lecture today. Today's lecture will be on Green's theorem in the plane, which is one of the most important integral theorems, and as we'll see has several different extensions to 3D. So Green's theorem in the plane is exactly what it sounds like. It's going to be in the plane or for in 2D for a two-dimensional vector field. So let's get into this, and we are going to start by saying we're going to consider what's called a planar vector field, which we've talked about before. Where F can be expressed as, because it's planar, it's two coordinates, P of xy and Q of xy. And we tack on a 0 for the third coordinate as well. But really we just want to think of this as a mapping from some domain in two-dimensional space into two-dimensional space, because it's staying inside 2D. And this is, remember, always going to be defined on some set. We'll call the set the domain set, where D is a subset of R squared, of two-dimensional space. And of significant importance to us for this theorem that we'll be talking about is going to be the curl of this vector field F. So recall that when we go to calculate the curl of a vector field in 2D, you can obtain that both of the x coordinate and the y coordinate are 0, and the z coordinate, or the z component of the curl, is the quantity partial derivative of q with respect to x minus the partial derivative p with respect to y. So the only rotational component this curl can have is around the z-axis, or about the z-axis, when we're considering a vector field it's a planar vector field, specifically the curl only points in the k-hat direction, or the k-hat component of curl is exactly this difference, dq dx minus dp dy. So this idea is going to be very, very important to us. So we'll start with the first statement of Green's theorem. What we're going to do is we're going to say that. So let's let the domain R be a bounded simply connected what this means is basically that it's free of holes. More advanced way of defining simply connected is that any curve C, and this is our domain R, any curve C in R can be continuously shrunk to a point that is contained in R. This is true for any curve. This is what simply connected means. That there's essentially no holes in the region R. And R is in general, we'll say, a subset of D. A subset of the domain of our function. This is our first set of assumptions. And then our second assumption is we're going to let the curve C be a piecewise smooth curve, the boundary of the region R. So C is the boundary curve that bounds the region R. Then the statement of Green's theorem is as follows. It's that the accumulation of the flux of the vector field F on the boundary curve C is going to be exactly equal to the accumulation of curl of the vector field F within the region R. It's the interior of the curve C. Oops, and I forgot to put one last assumption up here that is actually very, very, very important. So I'm going to add some space and add it up here. F is differentiable, assumed to be differentiable. In the domain D, for all points in D. And this is important to guarantee us the existence of this curl. So as long as this is true, though, these three assumptions are true, we have that Green's theorem in the plane is saying that the total circulation of the vector field around C is exactly equal to the double integral of the curl of this vector field in 2D. Now, a more standard way of writing this, and this is a much more standard way of seeing this, is to write it as written out in coordinates, in our coordinates. So in this case, this will be the closed contour integral around the boundary of P dx plus Q dy. And remember, if you remember back to our contour integrals lecture, this is an equivalent way of writing the contour integral. It's a completely equivalent notation. And we're going to see that for the proof, when we end up proving Green's theorem, this is going to be a nice notation to be using. And we see that this is going to be exactly equal to, in Cartesian coordinates, the curl of f is dq dx. So the curl of f dotted with k hat is dq dx minus dp dy. dy dx. Using Cartesian coordinates, dA is just dy dx. So both of these things mean the exact same same thing. We're essentially saying that the circulation of the vector field f is equal to the accumulation of curl inside the region. And this is a really, really nice theorem because essentially it's we can think of it as, in some sense, a generalization of the fundamental theorem of calculus from single variable calculus to multivariable calculus, so to vector fields. And this is one of the first main generalizations that we'll see. The idea here is that we're saying, we're equating in some sense a sort of derivative of this vector field f, the curl of the vector field f. We're equating that throughout the boundary, throughout the interior of this region R, to the action of the vector field along a specified direction on the boundary. This is saying the accumulation of the vector field tangent to the boundary is equal to the accumulation of curl over the region inside the region R. And it's also important to point out here that all of these curves are going to be oriented so that we're moving in a specified direction around the curve. So for instance, if this is our curve C and this is our region R, we're always going to be taking our integrals where R lies to the left as you traverse the curve, as you go around the curve. And it's always important to specify this orientation because we know that if you switch the direction of a line integral, you get the negative of that line integral, which will be very, very important coming up. So the proof of this theorem is really, really nice, and it's essentially just broken into two main parts. The first part, we consider what's called a standard domain, which is a simplified kind of domain R. But we'll see very quickly that we can actually generalize this fairly easily. So a standard domain we define as follows. Let's give a definition of a standard domain. I'll draw a picture to help us understand exactly what type of domain a standard domain is. So a standard domain looks like this. It's any domain for which when we draw a line through the domain, we get exactly 2 points of the domain. If I draw a straight line through the domain in either direction, I get exactly 2 intersection points, top and a bottom. And the idea here is that we can solve for a function of the top and a function of the bottom of the domain for any single one of these boundary curves, so to speak. So specifically, we can find, say, a partitioning of our domain. We'll call this point right here and that point right there. Call this point A along the x-axis, and this point B along the y-axis. We'll call this point C along the y-axis, or sorry, these are along the x-axis, these are along the y-axis. Call the bottom C and the top D. So this top function, the top boundary function, is a function of x. We'll call y is equal to y2 of x. And the bottom curve right here we'll express as y is equal to y1 of x. So y2 of x is the top of this region. This is valid for x from A to B. And y1 of x is the bottom. And again, this is valid for x from A to B. Likewise, we'll call the left boundary and the right boundary. So this curve right here, the left boundary and the right boundary, we'll call this left curve x is equal to x1 of y, it's a function of y. So we can always find these functions for a standard domain. And then we'll do x is equal to x2 of y for the right side of the domain. You might remember standard domains from your calculus, multivariable calculus class, where you define double integration. This is the first type of domain that you see, the simplest type of domain. So x2 of y is going to be the left boundary function, and x2 or x1 of y, x2 of y, x1 of y is the left boundary function, and x2 of y is the right boundary function. And again, this is for y from, both of these are for y from C to D. And you'll notice that I labeled points here. I'm going to label this point A, this point B, capital A, capital B, this point, the bottom point C, and we'll label up the top point D. Just for help in describing. So we can think of the boundary curve of this region. This is the region, entire region right here is the region R for this simple domain. So the boundary curve of this simple region, we'll call it capital C, like this. May be thought of as the union of the paths ACB and BDA or as the union of the paths DAC and CBD. Right, and it's important to expand upon these paths, kind of expand and remind ourselves that ACB is just the curve y1 of x. The path BDA is the curve y2 of x. But traversed in the opposite direction, so traversed in this direction right here. And likewise, the path DAC is the path x is equal to x1 of x, but traversed in this direction right here, so from D to C. And CBD is the path CBD, so from here to here, which is the path along the curve x equals x2 of x, of y. Both these are functions of y. And so noticing this is going to be the key to going through and proving this. So let's go through the first possibility. We'll really look at this in two steps. And step one is to look at this first possibility right here. So ACB and BDA. And we're going to look at the double integral over this region R of the partial derivative of Q with respect to, or P with respect to Y. Well, from our rules on double integration, this is the same thing as the integral from A to B of the integral from y1 of x to y2 of x of dp dy dy dx. We know that p is a function of x and y. This is the partial thing. Take the antiderivative of the partial derivative of p with respect to y and evaluate it from y2 to y1. So we know that this is going to be exactly equal to, from the fundamental theorem of calculus in 1D, the value of p at x comma y plus, in general, some general function g of x. That's the antiderivative of the partial derivative of p with respect to y is in general going to be the p of xy plus some arbitrary function g of x. But because we are evaluating this at y2 and y1, this g of x, when we plug in for y here, is going to cancel out in the difference. So this just becomes the integral from a to b of p of x comma y2 of x minus p of x comma y1 of x. And we know from our sum rule we can re-express this as the integral from a to b of p of x comma y2 of x dx minus the integral from a to b of p of x comma y1 of x and this is the key sticking point. What we're going to do is we're going to switch the bounds of integration here because we're trying to get this expression into the form of a closed line integral related to this function p right here. And sure enough, we can directly do that. If we reverse the orders of integration here, you notice that this is equal to negative integral from b to a of p of x comma y2 of x dx. Negative sign coming because we reverse the order of integration. This is the integral from a to b of p of x comma y1 of x dx. And this is equal to now negative times the line integral of p dx from b to a, going over this path right here, so going along y2. This is saying go from b to a, where x is b to a and y is y2 of x. That's just that top path. This is just the line integral from b to a along the path b dA. And added to this is going to be this integral right here, which is the line integral from A to B along the path ACB. And so the sum of these two line integrals is the closed loop line integral, or the closed line integral over the entire path C, capital C, of P dx. And so what we've shown is that whenever the conditions of Green's theorem are met for a standard region or simplified region, we have that the double integral of the partial derivative of any function p is the closed line integral around the boundary times -1. So negative the closed line integral around the boundary. And so a good exercise for you to do would be to go through this entire list of equations, right? But for dg dx. Right, so I'm going to say that you should check this next statement. And the calculations are very much the same, almost exactly the same, just with a couple different differences, mainly because the double integral now, you get r of the function d q dx dy dx is going to be exactly equal to the closed line integral, not negative, no negative, the closed line integral of c times q of q dy. So this is a big result, and this is a big result that you should check. It's very similar to the above calculations, just with a couple minor differences, but they're very small differences. And when we now add the first part here, this is step 1. This part will be step 2. When we add the results together, we get exactly what we want, which is that the closed line integral of p dx plus q dy over a boundary curve C is going to be equal to dq dx integral, double integral, plus negative dp dy, double integral, which is the double integral over r of dq dx minus dp dy, or dq dy, dq dx minus dp dy is right. Yep. This is dy dx. And this gives us Green's theorem in the plane. This is a super useful result. But remember this proof, the proof that we've done here, that I've just kind of done out and shown over, only works for a standard domain, or one in which we can express the top and the bottom as a function of the first variable, and the top and the bottom, or the left and the right, as a function of the second variable. Luckily, though, there's no reason to think that we can't somehow extend this, and sure enough, we can. And we can do it in a very nice way. So let's see how to extend this, and we'll do that by drawing a non-standard region. This is definitely a non-standard region because you have not just 2 points of intersection along this line, or any line here that you draw along Y. You have more than 2 points of intersection, and you can see that many other non-standard regions could be possible. In general, for a general region of space, it could be very many intersections. So the idea here is the following. What we do is we'll introduce curve gamma that cuts this non-standard region up into two standard regions. So gamma will be parameterized going up in this direction. So this is this cut gamma. And what we do is we consider what the line integral looks like and what Green's theorem is saying on the two sub-regions, the standard regions. In this case, we'll introduce a curve that is tracing along this first region right here, but doesn't quite touch gamma. It gets very, very close to gamma, and then splinters off. And goes straight up and around. So this first curve is consisting of an outward part. I'm going to call it C1 epsilon. In this inner part, to this line right here, I'm going to call gamma 1 epsilon. And we're going to do the exact same thing for the other piece. Now notice, before we draw the other piece, all curves that we draw have to have this orientation around the curve. The starting orientation that we started out with, so it's going around in this direction right here around the curve. Likewise, then we'll introduce a C2 epsilon going around and touching this boundary. Right here. So this is going to be called C2 epsilon, and this curve is gamma 2 epsilon. This straight line portion right here is gamma 2 epsilon, and this curve right here is C2 epsilon. Now it's important to remember that the ultimate boundary curve, the original boundary curve, is the boundary here, C. It's the entirety of the boundary. And the reason that we're calling these curves epsilon is because, or with a subscript of epsilon, is because we're going to define this distance right here. So the distance between gamma 1 epsilon and gamma 2 epsilon, the max distance, we'll define as epsilon. This gap right here is characterized by the value epsilon. And because these regions, each region surrounded by each one of these curves is, we'll call R, this one is R2 epsilon, and this region is R1 epsilon. We have that within each one of these regions, because they're standard regions, we can apply our theorem, Green's theorem. And Green's theorem applies directly from the proof on the previous our previous standard region proof for Green's theorem. So we have that the closed contour integral over C1 epsilon union R1 or gamma 1 epsilon, which is this curve and this curve of f dot dr is equal to the double integral over R1 epsilon of the curl of f dr and likewise for the R2 regions, the second region, we have that the line integral over C2 epsilon union with gamma 2 epsilon, or the line integral over this closed region right here is going to be the double integral of over the region R2 epsilon of the curl of f, and this should be dotted with k, which is the k hat component of curl of this 2D vector field. And it's important to think about what happens now as epsilon goes to 0. So what happens to these domains when epsilon goes to 0? So specifically, we'll consider what happens when we add these two expressions together and then take this limit as epsilon goes to 0. Specifically, when I add these two expressions together, we get the closed contour integral over C1 epsilon union C2 epsilon union gamma 1 epsilon union gamma 2 epsilon. So it's this is the combination, right, of the closed line integral over this curve right here and this curve right here. Of f dot dr and this is equal to the double integral over the union of the domains R1 and R2. And as epsilon goes to 0, so in this limit, as epsilon goes to 0, this curve gamma 1 epsilon is becoming gamma. This curve gamma 2 epsilon is becoming negative gamma, or gamma traversed in the opposite direction. And the curve C1 epsilon union C2 epsilon is just the curve C. So as epsilon goes to 0, this integral becomes the closed contour integral over the curve C union gamma, where gamma is the split, union the curve negative gamma, or gamma traversed in the opposite direction. And R1 epsilon union R2 epsilon becomes just the set R. The final step here is remembering how to simplify our line integrals. This is the same thing as the closed integral over C of f dot dr plus the open integral over gamma of f dot dr. Then the integral over minus gamma is negative the integral over gamma of f dot dr. All of this is equal to the double integral over the region R of the curl of f. And because these two values are the same value, they cancel out, and what we're left with is that the circulation of f is exactly equal to the double integral of the curl inside this region R, or the closed integral over the closed contour integral of p dx plus q dy over the contour C. The boundary of R is the double integral over R of the curl of the vector field f dotted with k hat. And there you have it. We've shown how to take the proof for a standard region and extend it now to non-standard regions. So this is a very, very big theorem, very, very powerful theorem, because essentially this is going to allow us to go through and actually generalize this even more. So it turns out that Green's theorem is powerful for a number of different ways, but essentially it's really powerful because it extends the idea of the fundamental theorem of calculus to more than one dimension. This is now to 2D integrals, where we have this nice combination of is dq dx minus dp dy, saying that this combination of this combination of two functions, q and p, of two functions of two variables, if we take the x partial derivative of q minus the y partial derivative of p, we're getting a measurement of the total amount of rotation in the region R. But what this is saying is the accumulation of that rotation is exactly equal to this line integral over the boundary of the region R, which is exactly intuitively the same as the fundamental theorem of calculus in 1D. It's very, very similar to it. So we'll see some more some more extensions of this a little bit later on. But for now, let's focus on an example problem, or a couple example problems, just to see in a couple short steps how useful this can be. So let's say we want to figure out the area of some region. This could be a very, very complicated region in two-dimensional space. In general, this is a hard problem. It's a very difficult integration problem. But it turns out that we can prove that the area of any region R is exactly equal to the boundary, or the line integral over the boundary of that region. Simply it's 1/2 times the closed line integral of negative y dx plus x dy. It's the line integral over c. So very often it's easier to evaluate this line integral than it is to evaluate the double integral, giving the area for that region. And we can directly apply Green's theorem here, because what Green's theorem is going to be is it's going to say, well, we're looking at the closed line integral of negative y over 2 dx plus x over 2 dy. So in Green's theorem, this is our P, and this is our Q, and so this is equal to the double integral over the region R of the partial derivative of Q with respect to x, which is 1/2, minus the partial derivative of P with respect to y, which is negative 1/2. And 1/2 minus negative 1/2 is just 1. This is just the double integral over the region R of 1 dy dx, which is exactly the area of that region. Let's see if we can apply this to see if this is actually making sense. And sure enough, it is definitely making very, very good sense. And we'll use this formula to get the area of an ellipse in a much easier fashion than we normally have to do it. And if you use elliptical coordinates, which are very similar to polar coordinates, it's not that bad. However, what I want to do is avoid doing the double integral. Let's try and think if we can get the area of the ellipse without having to use this double integral. So sure enough, we know that the area of the ellipse is going to be this double integral for the ellipse of 1 dy dx. And you can go through and evaluate that even in Cartesian coordinates if you really want to. But it's not very nice to do in Cartesian coordinates. It's much nicer to do in elliptical coordinates. However, I think it's even nicer to do using this formula that we've just derived in terms of just this line integral. So a single variable integral will give us the area of this ellipse. All we have to do is figure out how to evaluate the line integral, and this is, again, as we've been doing, reliant on the parameterization of the ellipse. So we can parameterize the ellipse. Remember, the ellipse is the equation x over a squared plus y over b squared is equal to 1. The ellipse is parameterized as x is equal to a cosine of t, y is equal to b cosine of t, which means that dx dt on the ellipse is negative a sine of t, and dy dt on the ellipse is, this should be sine. Just like the circle, only without a radius r. This is the x, either the semi-major axis or minor axis, and this is the semi-major axis or minor axis, depending on what the relative values of a and b are. So this is the correct parameterization of the ellipse, which means that this is going to then be b times cosine of t. It's a derivative of y with respect to t. This is just valid for t from 0 to 2 pi. And so now when we go through and try to evaluate this line integral from this formula, what we'll get is this area, the area of the ellipse, is going to be equal to the line integral from 0 to 2 pi of negative y over 2 dx, which is negative a sine of t dt. And we also have the dy term, so I'm going to bring the dt out, the outside of this sum, and plus x over 2, which is a cosine of t over 2 dy, which is b cosine of t dt. And at first you might be saying, oh, this is crazy, this is not making this easier at all. But if you look closely at the coefficients here, you're going to see that we have a 1/2 term common, you have negative times negative, you have b times a. So the area of the ellipse is going to be a times b over 2 times the integral from 0 to 2 pi of sine squared of t plus cosine squared of t, which is itself just equal to 1. And when we plug into this, this becomes ab over 2 multiplied by 2 pi And so our final value for the area of the ellipse is just equal to pi times a times b. But we haven't used any double integral at all to evaluate this. We've just used the fact that for this vector field, so for p equals negative y over 2 and q equals x over 2 for that vector field, by Green's theorem, the closed contour integral over any contour of this vector field is going to be the area of that region. So if we restrict ourselves to the ellipse and use the boundary curve, the integration becomes very, very nice and very, very easy. And this is typically, one of the typical uses of Green's theorem is to simplify integration. We might have the integration of a very, very complicated vector field. The double integral could be very complicated to evaluate. And if we do Green's theorem on it, we might be able to show that the line integral is much easier to evaluate. And you could have the opposite problem. For some functions, you might have a vector field where the line integral is looking like it's impossible to evaluate, but when you use Green's theorem to translate it into a double integral, the curl of the function could be very simple. It might simplify so that the double integral might be easier to evaluate. So Green's theorem is a very, very useful tool in that regard, and those are the two main big reasons that it's used for. We can also use it to prove things about curves, so prove certain physical properties, maybe about curves, or about the properties of curves that we've talked about before.